Hey everyone, it's Mr. Canfield. Today we're going to do L'Hôpital Part 2. Spell it however you want, pronounce it however you want. L'Hôpital, L Hospital, or Amberlance. No, ambulance, no, it's L'Hôpital, but whatever. I bigged up his name enough. Some of you guys think he's great just because his name is fun, but that's just because you grew up speaking English like me. Alright, so we're starting on example 12 today. Example 12 says take the limit as x goes to pi over 2 of secant x minus tangent x. So if we try at the outset to plug this in, secant and tangent both, secant's 1 over cosine, tangent sine over cosine. So the deal is, if I'm trying to find secant or tangent of pi over 2, if we remember that our unit circle is broken up, we say this is 0 and this is pi, right? And then this is 2 pi. So pi over 2 is straight up, it's 90 degrees. So what that means is this is the coordinate 0, 1. So I remember it goes cosine, sine. So 1 over cosine is going to be 1 over 0, which is going to be undefined, or some form of infinity. We're not sure if positive or negative, but we'll just say for argument's sake that's supposed to be a plus or minus, not a 2. Similarly, when we do this, we wind up getting 1 over 0, which is also, we're going to say some sort of infinity. So the problem is infinity minus infinity isn't one of our forms that lets us go to the hospital. Remember, the only way that we're allowed in the hospital is if we have a plus or minus infinity over infinity, or a 0 over 0. So because of that, if you try to go to the hospital like this, they're going to kick you out. So there's a joke in there. There has to be some kind of joke about like going to the hospital under the wrong pretenses and somehow getting in trouble. Like there's something there. I'm not there, but if you think of it, let me know, because I want to be able to tell this for years to come. Make people upset for years to come. So anyway, so we can't do L'Hôpital's rule, but we can do some manipulation. So what if instead we just talked about this a minute ago. This is 1 over cosine minus sine over cosine. So I just want to remind you, adding and subtracting fractions, if they have the same denominator, then that's like saying if I have a quarter and I add 3 more quarters, 1 quarter plus 3 more quarters. And I like using quarters because at least until the coin shortage, it was something that we all carried around in our pockets. That was a total of 4 quarters, or $1. And so remember that the way that works is the denominator stays the same. It's the top number that changes. So I actually could look at this and say this is 1 minus sine x over cosine x. So if you can't tell, I'm at home today, and Maeve is playing around. She's having a good time. So hopefully she doesn't get too distracting for you. So now if I go and I plug in pi over 2, I wind up getting 1 minus 1. I get 0 on the top. And on the bottom I get 0. And now I have 0 over 0. So this is my ticket into the hospital. Now I'm allowed to go. So now we'll take the derivatives. And so the derivative of the top is going to be negative cosine, and the derivative of the bottom is going to be negative sine. And now, well, the double negatives cancel each other out, but now when I plug in pi over 2, I'm just going back to this every time, right? So cosine is still 0, sine is still 1. Oh, cool, we get 0. Okay, so you might have been like, well, Canfield, infinity minus finity. Did I say infinity minus finity? Infinity minus infinity. Isn't that always 0? I kind of stepped over that. Let's go back and think about that really quick. Here's the problem. Infinity is this idea of something infinitely large. And with limits, the idea is that we're approaching. But if we're talking about something that's infinitely large, it's just growing and growing and growing. It never stops growing. But as it grows to be infinitely large, do these grow actually at the same rate? Are they actually growing infinitely large at the same speed? So one way we could kind of think about that is if we compared something like x squared versus 2 to the x. Are these traveling off toward infinity at a comparable rate in such a way that if we were to do some sort of limit where they were fighting each other, like doing one subtract the other, would we approach a situation where one infinity trumps the other infinity? I don't know if you remember, we've done things like x cubed versus x squared. We've looked at this before. Like if we look at x cubed, if we look at x squared over x cubed over time, the x cubed winds up being so much bigger than x squared as we go off towards infinity that the x squared essentially looks like 0. And sure enough, I mean, you can even cancel this. This cancels down to 1 over x. And 1 over x, as we go off to infinity, that looks like this. It looks like 1 over infinity. And looking like 1 over a gigantic number looks like 0, and it gets closer and closer and closer to 0. So now let's look at this situation, x squared versus 2 to the x. Well, let's start out with 1. So 1 squared versus 2 to the 1. Well, in this case, this is, it's 1 versus 2. But then what if we look at 10 squared versus 2 to the 10th? So 10 squared is 100. 2 to the 10th is 1024. And, so these are already, this is over 10 times more than that one. Well, what if I look at 100? 100 squared versus 2 to the 100th. So 100 squared is 100 with 2 more zeros, so 10,000. 2 to the 100, I don't know what that is. Feel free to try it in your calculator. I'm guessing your calculator says error overflow. If I remember correctly, the highest it can go is like 60s or 70s. Oh, I can't remember. It's been a long time. Oh wait, the DOI. 2 to the 100. Oh no, it can do it. Oh, it only has 30 zeros. Okay. 4 zeros versus 30 zeros. So even though if we approach infinity, both of these are going out and approaching infinity, but they're not approaching the same infinity. They're not approaching it in the same way. This is blowing up way faster than this one. And so because of that, if I was to wind up having like an infinity minus infinity in this case, where it was x squared minus 2 to the x, and we got infinity minus infinity, it wouldn't be 0 because of how drastically they interact. So we will definitely talk more about this in the future. And I understand that this might be a slightly odd way of thinking for you. The good news is, if you just remember, infinity minus infinity is inconclusive. I need to do more research. Like, you don't need to quite understand the principle behind it yet. It's one of the big ideas we talk about this year, though. We'll circle back to it over and over and over again. As much as BC Calc kind of goes all over the place, I also feel like it does a better job focusing on a couple main ideas. Okay, so now we're looking at this one, and if we do this again, we plug in 0, we get 1 over 1 minus 1, we get 1 over 0 minus 1 over 0, and you might go, well, 1 over 0, like, isn't it just going to be 0? And it's like, we can't necessarily be sure. So even though it's infinity minus infinity, and shouldn't that be 0, let's be careful and let's see what happens, and let's thoughtfully approach this. So unlike the last one, these two fractions don't have the same denominator. So if you recall back to whatever grade you learned adding and subtracting fractions, if we have a half plus 3/4, the way that we do it is we convert it so they both have the same denominator. So in this case, I just need to multiply the 1/2 by 2/2 so that the bottom is a 4. And then 2 plus 3, now I have 5 of these fourths. But when they didn't share something in common, like let's say we had 2/3 plus 6/7. Well, in this situation, neither of these denominators can turn into the other one. We need to find some common denominator. So I can multiply the 3 by 7. If I do that, I get 21. So I get 14/21. And this one I can multiply both of these by 3 and get 18/21. So now I have 14/21 and 18/21, giving me a total of 32/21. 21st, that's the way we should really say it. I rolled my eyes as I said that because I was like, I know someone's going to be annoyed that I'm saying it wrong the whole time. So here, I have this quantity and I have this quantity. I can't multiply this to turn it into that and vice versa, so I'm just going to multiply them by each other. If I multiply this by x over x, or x over x, multiply this one by e to the x minus 1 over e to the x minus 1, now we have this common e to the x minus 1 denominator. I'm left with x minus 1 times e to the x minus 1. So all that's going to be on top, right? And the bottom is just going to be this common denominator. And I can take the limit as x goes to 0 of this. So let's see. If I do that, well, let me plug in 0. Well, that's 0. 0 minus, I have 0 on the top. I want to be getting 0 on that. 0 over 0. Cool. We get 0 over 0. We're allowed to go to we're allowed to go to the L'Hopital. I am thinking that before I take the derivatives of the top and the bottom, I'm going to simplify them first. That's my own personal preference. I want to see if did Stu simplify them first? Yeah. He actually left out that step that I did there. I do have his answer guide up, but it's more just because I need the problems. Oops. So this is x e to the x minus x. So that's how I'm choosing to write the denominator. You could write it differently. He actually doesn't multiply out the denominator, but anyway, if you're wondering why I'm talking so quietly, my face is pretty close to the camera and I don't want it to be super noisy. So now when we use L'Hopital's rule, we will get, let's see, 1 minus the derivative of e to the x is e to the x, the derivative of 1 is 0. And then down here, we'll have a minus 1. I've got to do product rule with this, and there's no way around it. You have to do product rule either way, so this is just the way that I chose to do it. So I'll take the derivative of the first one, have an e to the x, then derivative of the second one, and leave the first one alone. All right. Now when I plug in 0, I get 0 on the top, right, because it's 1 minus e to the 0, which is 1 minus 1, which is 0. On the bottom, we get e to the 0 minus 0, e to the 0 minus 1, which is 1. The 0 goes away, minus 1. Oh, we get 0 over 0 again. But remember, it's okay to go to the hospital for the same problem multiple times. So we get 0 over 0. That means L'Hopital's is applicable. So applicable? Which one is it? All right, so the top turns into negative e to the x. The bottom turns into, well, that one stays there. This one I got to do product rule for it again, right? So, and it's just this again. That's an interesting derivative that keeps, like, it almost like recurs itself. Try to pronounce this. All right, anyway, the 1 turns into a 0, so we're here. So now, if I plug in 0, I get, let's see, I get negative e to the 0, which is negative 1, and then I get e to the 0 plus e to the 0 plus 0 e to the 0, which is 1 plus 1 plus 0, which is 2. Negative 1/2. So for this one, as we approach 0, the limit actually approaches negative 1/2. These two infinities wind up like fighting each other down to the half. I thought more deeply about it right now than I think I ever have, and my brain was just like, what? It's weird. It's weird. And I've done this problem a bunch of times before. I've thought about these things before, but it's still the mind contemplating infinity gets bewildered fairly easily. So there's no shame in being both amazed, confused, annoyed, and no, amazed, amused, annoyed. Yeah, by infinity. Okay, so let's try it again. Plug in 0. Cosecant. Cosecant's 1 over sine. So if you remember from earlier, back looking at our unit circle, 0 right here. Well, our point at 0 is 1, 0, and sine is 0. So cosecant of 0 is 1 over 0, which is, undefined or infinity. So now we've got infinity minus infinity. We've got another situation, surprise, where I've got to figure something out. So let's do it. Maybe I can 1 over sine minus 1 over x. Sure, there we go. This is the same kind of situation where different denominators, so I can multiply. So now my denominator is x sine x, and my numerator is going to be x minus sine x. So when we take the derivatives, we'll get 1 minus cosine x on the top. Oh, I haven't taken the limit yet. And in the denominator, we'll have to do product rules. So derivative of x is 1. And then leave the x alone and take the derivative of the second one. Okay, so now let's see what happens when we plug in 0. We get 1 minus 1. We get 0 on the top. We get 0 on the bottom as well. So we get 0 over 0. We have to do L'Hopital's rule again. Take the derivative of the top separately. This one's nice because it's 1 minus cosine, so the 1 goes away. The minus cosine turns to positive sine. Down here, the sine turns into cosine. Then we've got to do product rule again. So derivative of that's just 1 minus x sine x. And we're good, I think, right? Right? Because now we get 0 on the top, we get 1 plus 1 minus 0, or 0 over 2, or just 0. So in this case, the two infinities, as they're fighting, they wind up canceling each other out. Well, I just slid my foot along the floor, and it rumbled the camera. I didn't think about that. The camera's in a precarious place, otherwise I would show you Maeve sticking her tongue out right now. She's having a good time. All right. I'm going to do question 15, and then she's getting a little fussy, so I'll do 15, and then I'll break and then come back and finish the rest. Let's see. So 15. 15 says the limit as x goes to 4 to the x over x minus 2 to the x over x. Okay. X is going to 0, so we have 4 to the 0 over 0. So 4 to the 0, remember, that's 1. So we have 1 over 0 minus 1 over 0. Does this, do the infinity minus infinity, do they cancel each other out, or is there something else going on? So let's see what we can do, because right now we can't do L'Hopital's rule, but they have the same denominator. Can't I just do that? I mean, to me, that seems like the obvious move. If I do that, well, let's take the derivatives. Right, well, so, yeah, because we get 4 to the 0 minus 2 to the 0. We get 1 minus 1. That's 0 on the top, 0 on the bottom. So we get 1 on the bottom now. Let's see what these are. Well, remember that e to the x turns into e to the x, and these turn into themselves with an ln of their base multiplied on the end. Oh. Oh wait, this is fine. I was like, wait, they turned into 1 and 1 again. But so we're left with 4 to the 0 ln 4 minus 2 to the 0 ln 2. 4 to the 0 is 1, right? So we have ln 4 minus ln 2. Just a reminder, subtraction between ln's lets you combine them. So 4 over 2 is 2. Oh, I hope you guys did. Oh wait, no, I'm thinking of if you're watching this after the COVID year, like if I just am reusing this, hope you learned this in pre-calc. But anyway, ln2. So the natural log of 2. And if you remember that e to the 1, e to the 1 is 2.718. We're saying what power do I take e2 to get 2? So it's going to be like something a little bit less than 1. Let's see. At 0.693. So take e to the 0.69 blah, and it'll give you a 2. All right. So that's our second technique. Our final, I think this is the final technique we learned for L'Hopital's right now. Just to give you a little preview before I start doing this one. We're going to talk about the problem. Oops, it's an x. I wrote infinity because I was thinking about the next step. Think about this. Infinity to the 1 over infinity. This is saying infinity to the 0. Is infinity to the 0, which one wins here? Is it everything to the infinity power is 1, or is it infinity is so powerful that even though, because our exponent is approaching 0, it's not actually ever getting to 0. So is even though the exponent is small, does that does the fighting of these two quantities, these two ideas, does the infinity wind up beating out the thing that's approaching 0? So that's what we have to approach. We're going to learn a very special technique. The good news is it kind of always works the same, and we're going to say that we're E-ing it, or E the John, as some people like to say. But I'll be right back, and we'll look at that real quick. Here's Rosie being Rosie, seeing something outside. And here's Maeve. Hey, Maeve. Hey. So the cage is not locked. I'm like, oh wow, it looks like she's in a cage. No, it's just her little playpen. All right. So let's continue. Okay, so the random technique that we're going to talk about right now is, let's just start with something simple. Let's start with the number 4. What is the natural log of e to the 4th? Well, I just want to remind you, the natural log of e to the 4th, well, it has an exponent in there. What we can do is we can actually bring the exponent out front. If we have ln e like this, this is saying e to what power gets me e? Well, that's the first power, so this is actually 1. And so this is actually 4 in the end. And so something that we learned in pre-calc was the natural log of e to any number just turns out to be that number. Or any quantity even just turns out to be that quantity. So what would happen if we reversed this idea? What if we said e to the ln of 4. So this one's not as easy to see. So I'm just gonna show you. So just in case. So the reverse also works. And so we can talk about this for a minute and help you understand. Up here in the, so what does ln 4 mean? Well, this says e to some exponent gets me 4, right? So ln of 4 is equal to that unknown exponent. So it's saying take e to that unknown exponent. What do we get? Well, we get 4 because it's essentially by definition that's what we said would happen. So if I were to have a quantity like x squared plus 3x plus 2, and I said, hey, e to the ln, yeah, try again, can't fail, e to the ln of x squared plus 3x plus 2. Because of the way that natural logs and exponentials work, this, the e to the ln, it cancels itself out. We're just left with that inside stuff there. So we are allowed to take any quantity ever, and as far as I know, I guess there's some whatever. Just the ever is not like actually ever. Well, I take any quantity ever and just go e to the ln. The one aside for people who like to nitpick here, you can't take natural logs of negative numbers or even 0. So anyway, so the way that works here so you might be like, well, what's the point of this? This doesn't, like, why are we even talking about this technique? So when I try this, I get x to the 1 over x, I get infinity to the 0. So the kinds of cases we've seen so far, we've seen, you know, already ready to go to the hospital. We've seen turn it into fractions and go to the hospital. And now we're seeing e-it. And other options for e-it are infinity to 0, like 0 to the 0. There's a few others that we could run into. I'm drawing a little bit of a blank right now, but don't worry about it. So let's try e-ing it. So you might be like, wait, why would I do that, Mr. Canfield? This looks so much worse. So what we do, let's ignore the e and just focus on our exponent. Well, hey, this ln x to the 1 over x, hold on, it's an ln with an exponent inside. I can bring that exponent out front. So we're going to say 1 over x ln x. And you might be like, well, so? Well, remember, we're taking the limit as x goes to infinity. So this is now ln x over x. If we plug infinity into this, we get infinity over infinity. We can go to the hospital with this. So the top turns into 1 over x, because that's the derivative of ln, and the bottom turns into 1. And now we plug in infinity, and we get 1 over infinity, which is 0. So this, rewriting this as an e to the ln situation, makes it so that all of this, when we plug in infinity, this turns into 0. And now we're just saying e to the 0, which is 1. So in this case, infinity to the 0 did in fact equal 1. But we don't know if that's the case. They don't all equal 1 here. So this one's a little bit weird. Oops, I wrote the exponent. I got ahead of myself again. This time we get 0 to the 0. Is 0 to the 0 defined? Is it undefined? There's actually some back and forth about this in the mathematical community. But we don't need to worry about that right now. All we need to worry about is that since it's 0 to the 0, I can't do L'Hopital's rule because it's not 0 over 0. What if I were to try e-ing it? So again, just going to focus on the exponent. I kind of do this for my own organization. It helps me remember that I'm doing a problem within a problem. So the x is the exponent. I can bring it out front, right? Get x ln x. If I plug in 0 now, it's 0 times 0 times a negative infinity. That's not anything. So I actually have to do one more special trick. This is the one where we have to put the ln over 1 over x. That was just like what we did with that example 10 and 11. Yeah. So now I get infinity over infinity when I plug in 0. So now I can take the derivatives. And remember, 1 over x is the same as saying x to the negative 1 down here. So I feel like it's fuzzy. Is it fuzzy? Yeah, it looks a little bit fuzzy. I'm not happy about that. Anyway, so the derivative of the top will be 1 over x. The derivative of the bottom will be negative 1, x to the negative 2. And so again, we can flip this in a variety of ways. I'll show you my next step, and then I'll show you a workflow if you don't see it. So I got negative x squared over x, which turns into negative x. So you can do 1 over x divided by negative 1 over x squared, and then keep change flip, and then multiply straight across and get there. So negative x, so now I plug in 0 and I get 0. So that box turns into 0. And e to the 0 is 1. A lot of these end up being 1. Up next we have I'll be right back. All right. So this one says the limit as x goes to 0 from the plus side, from the right side, x to the sine x. Oh, I'm guessing, yeah. No, and this one didn't, but then the next one does too. Or the previous one didn't, but then 18 and 19 both do. So we get 0 to the 0 again. So we'll e it. If we e it, we get e to the ln of x to the sine x. So we'll, okay, with all the limit garbage out there. Okay, so let's look at this. If we bring the sine x out front, looks like that, right? Hold on. Yeah, no, that's any better. All right, so sine x times ln x, we still get 0 and times infinity. Like, it's not 0 over 0, but you know, if you've kind of picked up on the pattern here, we could write this as ln x over 1 over sine x. Oh, wait, and 1 over sine x is equal to cosecant x. So I could rewrite sine x times ln x as ln x over cosecant x. So now, when we go to infinity, we do, or 0, we get infinity over infinity. So we can go 1 over x, take the derivative of the top, take the derivative of the bottom. That's a negative, and it's the buddy system. So I know that it's buddied with cotangent. All right. Well, so that 1 over x, that can put the x down in the denominator. So now we can say this is 1 over, well, there's a negative out front. We get x cosecant x cotangent x. Okay. Let's, I'm just thinking out loud here. Well, 1 over cosecant is the same as saying sine. And 1 over cotangent is the same as saying tangent. So I can rewrite this as negative sine x times sine over cosine. There's an x down here. So we're going to say this is negative sine squared over x cosine x. I'm just trying things until I get to a form where, so now I get 0 over 0 again. So now I could do L'Hopital's rule again. All of these should have a limit in front of them, but I'm good. So the top, we'll take the 2 out front, leave the inside alone, then multiply by the derivative of the inside. Bottom we'll have to do, man, this is, I feel like it's going to wind up being 0. This is a lot of work for me just to get to be 0. I'm going to go see what Stu does and probably feel bad about myself after that. So I'll take the first derivative, I'll get cosine. Second derivative is negative sine. There we go. So I can plug in 0 here, and I get 0 on the top and 1 on the bottom. So this is 0. All of that just to turn the exponent into 0. So e to the 0, so I get 1. Let's see what Stu did. Stu, he... Oh. So it honestly, his wasn't much nicer. His might actually be worse than mine now that I'm looking at it. But what he did was he put sine x over sine x tangent x over x here. And instead of converting to sines and cosines, he just kind of left it here. And you get 0 over 0. So he takes the derivative at this point, did product rule at the top. Yeah, that's a good way to do it. Okay. $19. Wait. It appears that I've stumbled upon some A-B notes. Yeah. Let's move those out of the way.
My teacher's easily distracted.
All right. Limit as x goes to 0 from the right of sine x to the tangent x. So his formatting is ambiguous here. It really should say sine x to the tangent x, which is different than saying sine x to the tangent x. You know, like it's this is what he is intending for us to take this as, but the formatting is ambiguous. So when in doubt, blame Stu, you know, or me. When in doubt, blame anyone but yourself. So if I plug in 0, I do get another situation where it's 0 to the 0 to the 0. All right, so e to the ln sine x to the tangent x. It looks really bad, but if we bring the tangent out front and just, you know, like I've been doing with these, just focusing on the exponent. So can't we just say this is ln sine x over 1 over tangent x? Which another way to write that is cotangent x. So if I do that, the derivative of the top will just be 1 over sine x, right? Oop, chain rule, times cosine x. All over derivative cotangent, well, it's a negative, so its derivative is it's one of those buddy ones. Its derivative is cosecant, so it's cosecant cosecant. Oh, this is nice. This is really nice. You might not see it yet. This is really nice. Because now there's a cosecant squared on the bottom. So we can just flip that up to the top now. I'll do this in slow-mo, but on my own paper I would just flip this quickly. Divided by negative cosecant. Remember, negative cosecant is negative 1 over sine squared. So divided, keep change flip. So negative. I had double negative there by accident. Negative sine squared over 1. So now I have negative cosine x sine squared x over sine x. So the squared and the sine, so cancel. We got negative cosine x sine x. Yes, I know my problems go over this way and then down. I don't know what to do about it. But now I can plug in 0 and get 0. It's a little bit of like, you go through all this and it's just, okay, so it's e to the 0. This is 1. Cool. Alright. 2 more. I'm out of paper. Here's paper. The limit as x goes to infinity of 1 plus 1 over x to the x. I actually know this one. This is a formula I had memorized in high school. This is very, very close to an interest formula. So I already know the answer. It's the compound interest formula, more or less. So anyway, plug in infinity, we get 1 to the infinity. But remember, the inside is approaching 1. It's not actually 1. It never actually gets to 1 because we never get to infinity. So it's getting closer and closer and closer and closer to 1. This is getting closer and closer and closer and closer to infinity. So does it wind up just looking like 1 to the infinity would actually look, or does it look like what a little bit more than 1 to the infinity would actually look? So anyway, here we go. Here we go. We can E it. And if you're like, that's awful, yeah, no. Bring the x out front, ln 1 plus 1 over x. Wait, so it's ln 1 plus 1 over x, woo, over 1 over x, right? So now I get infinity, infinity over infinity. Let's go to the hospital, woo! So now I can do 1 over 1 plus 1 over x times the derivative of the inside. So this is x to the negative 1, right? So it's negative 1 x to the negative 2, or just negative 1 over x squared. So oh, what's the derivative of this? Literally the same thing as that. Well, would you look at that? What happens when you plug in infinity now? Don't get 0 this time, do you? Now you got 1 over 1 plus 1 over infinity, which is 1 over 1. Our answer is E. This is a famous result. some cultural context for you if you want. When we're talking about compound interest, the idea that you're getting a certain amount of interest every year. If you throw in R and then T here, that stands for the interest rate, and that stands for how long you do it. This is the compound interest formula. They usually use N instead of X, but regardless, the idea is if instead of saying, hey, every year you're gonna, I think the R has to go down here as well. But anyways, now it's a compound interest formula. So instead of, let's say I've got a 10% interest, which would be amazing. Instead of giving me that 10% interest at the beginning of the year, why don't you give me 5% halfway through the year, and then at the end of the year give me the other 5% on the but every time they give you that 5%, it's on the money you currently have. So they give you a little bit of money, and so you'll have a little bit extra the second time around. And then they were like, wait, instead of doing it twice a year, let's do it like every month. And so they'll break that into that 10% into 12 equal pieces, and they'll give you a little piece of that interest every month on your current money. And people were like, well, what if we just keep on doing this? And you see that the smaller you break it up, the more often you, what they call compound, the more often you compound, the more money you get. And it just keeps on going up and up and up, compound more, compound more. And so what they did was they took the limit as the number of times you compound approaches infinity, and it turns out that the most possible that can happen is E. So that's one place that E naturally occurs. Last one. 21. 21. No, is it 21? Is that? All right. So is it the same deal as before? We get 1 plus 0. Yep, we get 1 on the inside. We get infinity up here, 1 to the infinity. If we E it, e to the ln, e to the x plus x to the 1 over x. Well, let's just look at the exponent. Do what we've been doing. Wait, this, I'm like, this seems like it's going to be harder because it looks easier to start out. Why is he giving me an easy, like that? Stu, I don't trust you. Oh. No, I get ln1, right? ln1 is 0. I get 0 over 0. I can do L'Hopital's rule. So that's 1 over e to the x plus x. And then I got to multiply by the derivative of the inside. So I'll just put that on the top. E to the x plus 1. I don't need to put that in parentheses. All over 1. Oh, so this is just e to the x plus 1 over e to the x plus x. Now when I plug in 0, I get e to the 0 plus 1 over e to the 0 plus 0. I get 2 over 1. I'm just flabbergasted. E squared. Okay, so now there are 27 homework problems, and you hopefully have done, 10, 11 of them. All right, hope this was helpful. Bye.